Have you ever wondered why things have mass? Why your body has weight, or why moving an object requires effort? At first glance, it seems like something simple. But for a long time, this was one of the biggest mysteries in modern physics. The answer began to take shape in 2012, with a discovery that caught the attention of the entire world: the Higgs boson. A particle that not only completed a theory, but helped explain how the universe built everything we know. In the universe of subatomic particles, appearances deceive. Some of them, according to calculations, shouldn't have any mass at all, yet experiments showed otherwise. This contradiction led physics to a dead end. After all, would mass be an essential property or the result of some kind of deeper interaction? Such a question opened the way to a surprising idea: an invisible field, present throughout all space, capable of influencing each particle differently. In this video, you'll discover how the Higgs field works, the role of the Higgs boson, and why this discovery is so important for modern physics. We'll also understand how everything connects to the Standard Model and the structure of the universe. And more than that, how this understanding touches fundamental aspects of existence. If reality were a construction game, the Standard Model of particle physics would be like the manual that describes the fundamental pieces. It explains everything that makes up the visible universe, from the most distant galaxies to the particles that form the air you breathe. Within this model, matter is made of particles called fermions, like quarks and leptons. Quarks form protons and neutrons. Leptons include the electron and the discrete neutrinos, which pass through your body every second, almost without leaving traces. The forces that keep the universe together also have their own representatives. These are the bosons, which function as messengers of fundamental interactions. The photon transmits the electromagnetic force. The gluon is responsible for the strong force, which keeps quarks together in the atomic nucleus. And the W+, W-, and Z0 bosons are behind the weak force, involved in nuclear reactions, like those that occur inside the sun. Everything fit together well, until a persistent question caught the attention of physicists. These particles, which should be elements without mass, showed themselves surprisingly heavy in experiments. Such a discovery created a contradiction with the Standard Model itself. How could a theory so precise fail at something so fundamental? It was as if an invisible gear was missing from the mechanism. Faced with this problem, scientists began to consider a new idea. Something that couldn't be seen directly, but that would be everywhere, influencing the behavior of particles without anyone noticing. For a long time, physicists believed that some fundamental particles should be exempt from mass. That's what the mathematics indicated within the Standard Model. However, experiments told another story. Particles like the W+ and Z0 bosons not only had mass, but this characteristic was significant. Such a situation put the consistency of the entire theory in check. The question that arose was inevitable: is mass a natural property of particles, or does it arise from some deeper mechanism? This fundamental question led to another reflection, even broader. Are we seeing everything that exists? After all, the Standard Model, however precise it may be, doesn't explain everything. Gravity, for example, is still a force that remains outside this theoretical framework. The graviton, which would be the particle responsible for transmitting it, is just a hypothesis. And while the other forces have well-defined messenger particles, gravity continues to be a mystery within particle physics. Considering this gap, scientists began to consider that mass might not be something that a particle possesses by itself. Perhaps it was the result of an interaction. Something like trying to cross a thick liquid. The stronger this resistance, the more heavy the particle would seem. This new perspective changed the way physics understands matter, and what seemed to be just a theoretical adjustment ended up revealing a new layer of the universe. An invisible field, present throughout all space. Imagine a fish swimming in an ocean. It's surrounded by water but doesn't see it. Similarly, the Higgs field is everywhere, even where there seems to be nothing. Subatomic particles move within this invisible structure all the time, and it's the way each one interacts with this environment that determines whether it will have mass or not. Some pass through with ease. Others feel resistance, as if they were dragging something. Another useful comparison is to think of a person trying to cross a crowd. An unknown figure passes almost unnoticed. A celebrity, however, causes commotion, attracts attention, and has more difficulty moving forward. The same process happens with particles. Those that attract more attention from the Higgs field acquire more mass. A good example is the top quark, which interacts intensely with the field and, therefore, is one of the most massive particles we know. On the other hand, some particles practically ignore the Higgs field. The photon, for example, doesn't interact with it. Exactly for this reason, it has no mass. This selective characteristic of the field is what makes physics so fascinating. It shows that mass is not something absolute. In fact, it's a consequence of an interaction, an effect of the invisible environment that fills the entire fabric of space-time. And precisely this understanding led to an intense search for something that could prove that such a structure really exists. If the Higgs field exists, then it can be disturbed. And when such a disturbance happens, an excitation arises, a kind of local wave. This specific ripple is what we call the Higgs boson. Detecting this particle would be proof that the field is also there. However, such detection wasn't simple. It was like trying to see a single drop in a stormy sea. To overcome this challenge, scientists built one of the most impressive machines in history, the Large Hadron Collider, the LHC. In this gigantic equipment, protons are accelerated to speeds close to that of light and collide with enormous energy, recreating conditions similar to those of the Big Bang. These powerful collisions generate a series of particles, many of which last less than the blink of an eye. Among all this rain of particles, the Higgs boson could emerge. The analysis work required extreme precision. The signals were subtle, almost camouflaged amid an infinity of other events. Even so, scientists knew exactly what to look for. Finally, in July 2012, the discovery happened. The detectors identified a pattern consistent with the existence of the Higgs boson. The level of statistical reliability surpassed 99.9%. It was enough to announce to the world that the particle had been found. Such a discovery completed a gap in the standard model and crowned decades of research. The following year, in 2013, Peter Higgs, the physicist who had predicted the particle in the 1960s, received the Nobel Prize in Physics for this extraordinary contribution. The finding of the Higgs boson showed something profound. Mass is not a fixed property of particles. It arises from a relationship. That is, it's the result of interaction with an invisible field that fills the universe. This understanding changes the way we understand reality. After all, without mass, there would be no atoms, no molecules, and, consequently, nothing of what composes matter as we know it. The Higgs field itself is silent, but essential. It is exactly this field that makes the existence of the physical world possible. With this revolutionary discovery, the standard model became more complete. Finally, the last piece of the puzzle was put in its place. Despite this, many questions remain open. Gravity is still outside the model. The graviton, which would explain this force, remains hypothetical. Furthermore, we don't know how the Higgs field behaves on cosmic scales. Is there any connection with dark energy? This question represents one of the great frontiers of current physics. Clearly, there is still much to explore. Beyond the scientific implications, there is also a broader dimension. The fact that mass is a relational effect invites us to reflect on the role of interactions in the construction of reality. Nothing exists in isolation. Each particle is only what it is because of the way it connects with the whole. This particular view brings science closer to an ancient philosophical intuition, that everything is interconnected. Possibly, the next step is to understand how these connections shape the universe on scales we still cannot reach. In summary, the search for the Higgs boson was more than a scientific hunt. It was, in fact, an attempt to understand why things exist the way they are. Discovering that mass is the result of an interaction with an invisible field transforms our view of matter, physics, and even existence itself. Curiously, what cannot be seen is precisely what sustains everything we see. And such reality reminds us how much we still have to unravel in the workings of the universe. Probably the greatest lesson is that, behind every phenomenon, there is a network of invisible relationships. Matter itself only forms because there is resistance to movement. This specific resistance only exists because of a field present throughout all space. And the field only reveals itself because we dare to investigate. Each discovery opens new doors. In reality, each answer is actually an invitation to a new journey of questions. And had you ever thought that mass is not something a particle possesses, but rather something it acquires when moving through space? What else might be shaping reality, even without being perceived? If these questions intrigue you, subscribe to the channel and activate notifications so you don't miss the next episodes, because knowledge is just the beginning.